Whenever we talk about nonlinear systems, people are a bit afraid. But we will see that actually dealing with nonlinear systems is not at all difficult. We can extend almost the same theory which we are using for linear systems to nonlinear systems. This is one of my favorite subjects. Also, I very much favorite subject, this nonlinear systems. So, first lecture, I will discuss the features of nonlinear system, the characteristic of nonlinear systems. Then we will study stability. Then in the third lecture, we will study steering mode controller. Tomorrow, we will study about the feedback linearizing controllers. Little bit. If you go to any textbook or any place, people will say all the systems are nonlinear to certain extent, right? They will say it is written there, right? What I want to say, the system is never a linear system or a nonlinear system. That point, please be clear. A system is a system only. System is a system. It is neither a linear system nor a nonlinear system. It is, if it behaves linearly, you can consider at that time it is a linear system. If it behaves nonlinearly, then it is a nonlinear system. Clear? I can give an analogy. We cannot say whether a person is a good person or a bad person. It has nothing to do with the person itself. Right? If he behaves properly, then we say it good. If it behaves bad, right? But if you go, because you are all academics, and if you say that you ask the students the question that what is a nonlinear system, and their answer invariably throughout the world, you are going asking the question, the people will say a nonlinear system is that system where the principle of superposition does not hold good. It is not applicable, right? They will say, this is the, all students answer it. But that is partially correct. Even for the linear systems, principle of superposition also does not hold good. In the linear system, suppose a linear circuit, if you are calculating the voltage and current at different points, then you can apply the principle of superposition of multiple sources. We all have done it, right? For calculating the voltage and current, the principle of superposition holds good. But if you want to calculate the power, even for the linear circuit, doesn't hold good. Because power is a quadratic function. Power is a quadratic function of resistance. Remember this thing, linear circuit, if you calculate the voltage or current at different points by multiple sources, for each source you calculate the current, then add them together, that's fine. But power, no. You cannot do it. So because power is a quadratic function of the variables, right? So even for linear systems also, the principle of superposition does not hold good while calculating a power relation, right? Just like I give an analogy, Amresh Puri is a typical Bollywood actor. When you talk the name of Amresh Puri, people think that he is a villain, right? Which is not true. Sometimes he has also acted character role, right? So you cannot demarcate. You see, the way he behaves, right? I'll give an another example here. Very good example, all of us we give it. Saturation nonlinearity. This is the phi I characteristic. We say it is nonlinear, right? But it's not, you cannot make a general statement like that. Because if you operate within this zone, when the current is less than this, system is linear. The moment you operate beyond that, then the nonlinearity sets in, right? So it all depends where your operating point is, how you are operating. That decides whether it will behave nonlinearly or linearly, right? So first point is important because the academics see system is system. There is nothing like linear system, nonlinear systems. It all depends on its behavior. Clear? Okay. First point is the principle of superposition doesn't hold good, but with this constant. Very standard questions we ask, y is equal to mx plus c. Y is equal to mx plus c. Linear or non-linear? Linear, right? Apply principle of superposition here. You apply principle of superposition here. X1 will give you y1 is equal to mx1 plus c. X2, y2 is equal to mx2 plus c. Okay? x1 plus x2, x1 plus x2, what it will give? Can you add them together? If you add them together, it will be m into x1 plus x2 plus 2c, right? Which is not equal to y1 plus y2. So principle of superposition doesn't hold good for y is equal to mx plus c. Y is equal to mx plus c is not a linear. It is coming under the class of systems we will study tomorrow while doing with the feedback linearizing controller, affine class of systems. So mx plus c, remember, very standard academic questions. Y is equal to mx plus c is non-linear, right? That is not important. Stability we will discuss next lecture, so I am not emphasizing here. Linear system stability depends only on system parameters and not on initial conditions. But nonlinear system stability is different. We'll see. I'm not telling now. We'll see in next lecture. Why to waste time here? Important point is this point. Number 3 point is the most important point, which is not being emphasized in the nonlinear literature. Energy transfer takes place at a different frequencies. And that is a serious thing which I will tell you now. What is the meaning of that? The meaning is here, you see here. This is a square law nonlinearity, see here. You apply an input of sine omega t. The output will be a DC component and a 2 omega component. Do you see it? If you apply sine omega t here, there is a square law. So Ey is equal to u square t, that is equal to a square sine square omega t. That is equal to a square by 2, 1 minus cosine 2 omega t. What is the frequency of that component, yt? What are the frequency of that component? One DC component and 2 omega component. Do you understand that? See here, this term, it has got a square by 2 into 1 minus cosine 2 omega t. What are the frequencies? One is constant and this is 2 omega, right? 0 and 0 and 2 omega, right? What is the input frequency? Input frequency is omega. Input frequency is omega. The output frequency is 0 and 2 omega. Square law, right? So energy transfer takes place at a different frequency. What is the meaning of that? If it's a linear system, I will elaborate this point shortly, 1 minute. If it's a linear system, you apply A sin omega t, you will get some magnitude, doesn't matter, B sin omega t plus minus phi. If omega is here, you will get omega, right? Nonlinear systems, no. Nonlinear systems, you apply omega, you may get some different frequency component depending on the nature of the nonlinearity, right? Why it is so important? Why it is so important? I will tell you one example here. You know the oil rigs, ONGC here, Oil and Natural Gas Commission, ONGC, in the offshore oil exploration, there is oil rigs, right? The similar type of oil rigs in Europe, you will find above, they say North Sea, above Scotland, okay? And beyond that, there is quite a lot of oil rigs. They explore the oil. Okay. That is Norwegian government, they have got oil rigs there. This is the problem. I have not solved it. There is one student of Steve Billings who has solved it, and Steve has got that. That's very important observations. You see the rigs is there. Oil rigs, you have seen it. Oil in the structure, right? 4 cylindrical structures, cylinders, and this rig. Those people found that when the sea is very calm, there is no turbulence in the sea, okay, there is a severe vibration of the rig, which is, but whenever the sea is turbulent, there is no vibration. This is a real paradox, yes or no? This is quite paradox. When the sea is calm, absolutely calm, the wave is going at very slow rate, the rig vibrates. Whereas, when the sea is turbulent, there is no vibration. What is the reason? They collected data, wave force data, that wave is impinging on the rig structure, and they collected data, they found the model. I think Steve has done it, Steve Billings, my supervisor, with some student. You know why it's vibrating? They found the model between the wave force, okay, and the wave velocity, all these things. It is a nonlinear model. When the velocity, the sea is turbulent, okay, with that input, the resonant frequency changes from, say, I think about 0.7 hertz or a radian to 0.01 or 0.7. See, the resonant frequency changes because the model says 0.07. So when the resonant frequency changes to 0.07, so when the sea is calm, 0.07 means almost calm. See, you got a point, physical meaning. 0.07 radian means very low frequency oscillation. Sea is very calm. That input is impinged on the rig vibrates, because that coincides with the resonant frequency. Got a point? So usually you will find if people are working on motor control, see here, like this. Suppose there is a cascade system, that is one system here. This is another system, system 2. This is another system, system 3. I'm just giving an example. This example is very important. Suppose you know the resonant frequency of this one and this one and this one. If you know the resonant frequency, what you will do? You will not excite the system at that frequency, right? Clear? Now, the problem is, you do not know which type of a nonlinear element is there in those systems, right? Suppose I know the resonant frequency here is omega 1, here it is omega 2, and here it is omega 3, right? I know it. So what I will do, I will not apply any input having frequency omega 1, omega 2, omega 3, there. So what I did, I apply a signal of frequency omega 4. If I apply a signal of omega 4, it does not coincide, it will not resonate, clear? But because of nonlinearity which I do not know, suppose this omega 4 is giving rise to some frequency, you see, suppose this omega 4 generating some frequency omega 2 and omega 3. Suppose, because just like I told you, omega is generating 0 and 2 omega, right? This omega 4 is generating omega 2 and omega 3. So these two systems will resonate. Got a point? So whenever there is a cascading system, this happens in the power electronics drives. Power ABB drives, it is driving these motors and the nonlinear device. You do not know which frequency is generated. If that frequency coincides, not necessarily resonance. If the frequency is very close to resonance, the amplitude will be high. Got my point? Resonance, there is no need of resonance to occur. If the frequency is very close to the resonant frequency, the amplitude of oscillations will be high. Right? So therefore, this energy transport takes place at different frequencies is a serious issue. It is really a serious issue. You must be very careful. And normally, in the academics, we don't emphasize on the energy transfer aspect, right? So this is the point. Now see here the cubic nonlinearity, again another example. I apply sine omega t, then I get sine omega t and I get a 3 omega t. I applied omega t, in the output is giving omega and 3 omega. Okay? Energy transfer takes place at different frequency. Right? Now you understand the physical meaning of that. What is the meaning of this? Is typical happens not only in we are human beings. You tell certain things to somebody. Have you seen the talk of the ladies? Not the ladies talk. Actually, we said ladies talk. Actually, it's not ladies talk. Everybody's talk. I will tell you, Sonny, you see, I am telling these things to you. Don't tell to anyone. Keep it with you. If by any means you tell someone that I am telling to you, don't tell to anyone, you will find within 5 minutes he will tell to everyone. He will tell others, okay, you see, Dr. Swami told these things to me and he told not to tell anyone what I am just telling to you, but you don't tell anyone. You got a point? This is the energy transfer. Takes place at different frequency. You see, you tell certain things. Then this fellow will transfer at different frequency, something he, then that fellow will transfer with certain, you got a point? I give in Odisha, there is a Paradip port in Odisha. So the question has come in the examination that in school, which day the Independence Day comes? So people say, one student has written August 15th. 15th in the Odia language, I think Pandar. August Pandar. Pandar means 15. One fellow has written August Pandar. So another person, he copied it. But Pandar is not a term, he's Pandar to Bandar, port. So he wrote, Independence Day is August Bandar. The third person say, how August can be Bandar? It is Paradip Bandar. Now Independence Day is Paradip Bandar. You got a point? How this energy transport takes place at different frequency and it changes. Right? This is a typical characteristic of the system and you must be very careful about these things. Interchanging the cascading elements. In linear systems, if there is a cascading connection, you can interchange G1, G2, G2, G1. But it is not the case with a nonlinear system. You cannot just interchange this to that. Okay. Say, this, but this is not very important, but I will tell. Number 5 we will discuss after some time. Multiple isolated equilibrium points. I will discuss in today itself in this lecture. A nonlinear system, linear system has got only one equilibrium point. Remember, linear systems, no matter how complex it is, it has got only one equilibrium point. Again, repeating the point, linear systems has got only one equilibrium point. Linear systems cannot have multiple equilibrium points. Nonlinear systems can have multiple equilibrium points. Not that always it has got multiple equilibrium points. Okay. It can have multiple equilibrium points. Right? And multiple isolated equilibrium points. Okay, nonlinear system can have more than one isolated equilibrium point. This point can have. You see, I am writing see the wordings here. I am not saying that nonlinear system has multiple equilibrium points. Can have. There are nonlinear systems which has got only one equilibrium points. But most of the nonlinear systems has got multiple equilibrium points. And I will tell you what happens to these things later on. Today itself. Okay. Finite escape time means it can go to infinity within finite time. Whereas linear systems will go to infinity infinite time, but it has no meaning actually. That number 5, 6 point is a academic discussion because infinity is the 5 time constants, I told you, engineering infinity. So, multiple isolated equilibrium points. It has, linear system has got one equilibrium point and nonlinear systems can have multiple equilibrium points. Limit cycle oscillation. This is important. Let us first understand why oscillations occur. Unless that understanding is clear, you cannot understand anything. Why oscillations occur? Remember, for oscillations to occur, no matter it's a linear system or any system, there must be exchange of energy. There must be exchange of energy. For oscillations to occur. This is a LC circuit. This is a LC circuit. Okay? Now, if you inject certain amount of energy either to the capacitor or to the inductor, right? And leave it free. There is no input here. You see, I am not applying any voltage here. Just apply the impulse input, inject some energy, leave it. There is no resistance here. So what will happen? Then the magnetic energy which is stored in the energy which is stored in the magnetic field of the inductor will be transferred to the capacitor electric field, and then because there is no loss, there is no resistance here, then it will again transfer to inductor. Okay? So this continues. Exchange of energy, the RL circuit will not oscillate. There must be exchange of energy, otherwise not. Right? Now here, what happens? Limit cycle oscillations. This oscillation is a bit different. This oscillation is different. To understand oscillations, I will tell you one thing, which I tell it in different context. But this is India, I can utter those words here, because you can understand. Typical example of oscillations. Friendship. Who can become good friends? Chanakya has told these things. Exactly equal to the oscillations here. There are 6 characteristics. First is dodate pratighunnati. 2 people will be friends if you give something and he also gives something. You give him some present, gift, in his birthday, and he also gives you some present. That is exchange. I give, you give. Okay? Guhyamakhyati puchyati. You tell your secret to him and he also shares his secret. Then only you can become friend. Not that you will tell your secret and he will not say anything. No. Friendship will not last. Bhukte bhojayate chaiva. You ask him to come to a restaurant for dinner and he also calls you for dinner. You give him some food, treat him. These are 6 characteristics. This is a clear example of the exchange, you exchange. Okay? So oscillations to occur, similarly there must be exchange of energy. There must be exchange of energy. Then only oscillations will occur, otherwise not. Here, oscillations will occur because inductance exchange energy to capacitance, capacitance exchange. These type of oscillations in linear systems is different than the oscillations which I am going to talk, limit cycle oscillations. Limit cycle oscillations. Now first let us see what is happening. Then I will come back again. Dampers, damper windings, dampers in vehicles, okay? Suppose you drive in a good car and in the low variety car, you feel not comfortable. Why is that? Because you know the spring, the damper is not of good quality, so damping is there. Okay. Now let us see this equation first. Mx double dot plus bx square minus 1x dot plus kx is equal to 0. Let us see this equation, then we will discuss all these things. What is the damping? Damping, the usual equation is mx double dot plus bx dot plus kx, 0. The coefficient of x dot is the damping term, right? Coefficient of x dot is damping term. The coefficient of x dot here is b. The coefficient of x dot here is what? B into x square minus 1, right? So damping, usually what happens, it takes out energy. It takes out energy. Now if suppose x, the amplitude, displacement is less than 1. Suppose displacement is less than 1. If displacement is less than 1, what will happen? X square minus 1 minus. So that means negative damping. If x is less than 1, b into x square minus 1 is less than 0, right? Damping is negative. Usually damping is positive, or whatever you may say it, right? So instead of taking out energy, it will put energy into the system. it will put energy into the system. So the moment energy is put into the system, the amplitude of oscillation, see, a displacement will increase. Now once it is increased beyond 1, it becomes positive. So it will start taking out the energy. You got a point? So sometimes you put energy, and the moment you put the energy, X will increase. Now after that it increases, it will take out energy. You got a point? So over a particular period, sometimes it is positive, sometimes it is negative, right? So the effective damping will be 0. Let me tell you, what is the damping here? What is the damping here, can you tell me? LC circuit, what is the damping? Damping is provided by resistance. Is there resistance here? Damping is equal to 0. Damping is equal to 0, system oscillates. Okay? Now here, things is different. Sometimes the damping is positive, sometimes the damping is negative. The effective damping is 0. Okay? Effective damping is 0. So it will oscillate. Okay? But that's the difference. Damping is 0, pure oscillations. Effective damping is 0, limit cycle oscillations. Why the difference? You do not earn any money. You do not earn any money, your bank balance is 0. Case number 1. But you earn 2 lakhs and also you spend 2 lakhs. And your bank balance is 0. Are the same. From bank balance perspective, a person does not have any money, he doesn't earn anything, his bank balance is 0. Another person, he earns 1 lakh, spends 1 lakh, his bank balance is also 0. These two people are the same. One is a bloody beggar, another is a bloody scoundrel. He doesn't know how to manage his finance. 1 lakh, got a point? Two things are different completely. Limit cycle oscillation is like that. Effective damping is 0. Effective saving is 0. Effective saving is 0. Here saving is 0. Right? And another thing is there an input there? Is in this equation? Is there an input? Mx double dot bx square minus 1 x dot plus kx is equal to 0. There is no input. Self-excited. Self-excited oscillations. Okay, what is self-excited? I will give an example. When my son was studying in school, I used to, on the way to university, I used to drop him in the school. Then nearby I parked my car. Parking is you cannot park anywhere in foreign countries. Your car will tow down, but there are lots of parking. I park a car and then I walk down. 2 kilometers I walk down to university. Every time, almost every time, not while going, while returning from the university, I come and I pick up the car and I come home. I found one particular person, I still remember that fellow, with a jean, with the different types of dress, a hippie type of dress. He will be just talking something. Just talking. Self-excited oscillations. Nobody is there. Nobody is there. Okay? It will be around say 4 o'clock or 3:30. I usually leave the university at that time. Okay? He will be talking. I always give this example to the students. I told her I parked my car in the Mount Redon Road and I found a person in the Kid Street coming and talking like this. Self-excited oscillations. The limit cycle oscillations. Got a point? So limit cycle oscillation is a very important phenomenon. And it occurs for a system, nonlinear systems. The characteristic is it is self-excited, no input is necessary. First point, there is no input necessary for the oscillations. And second point, the effective damping is 0. Sometimes damping is positive, sometimes damping is negative. Okay, clear? Very important phenomenon, limit cycle oscillations. and is different from the common oscillations in linear systems. LC circuit also oscillates, but that's different. We'll see today itself. No, that you cannot say. We have to determine by different ways. Standard ways you can determine. Otherwise, by analytically you cannot determine. Analytically you cannot determine the frequency of oscillations. Okay, we'll come to that point. We'll see how it will be. Chaos. Chaos, if this is the nonlinear system space, if you divide this is the entire system, space is nonlinear, the chaotic systems will be this much. Very small percentage of nonlinear systems behave chaotic, right? Very common thing, very common, we have seen it. PhD students, okay? You ask them, you perform this experiment or you do these things, and they will get some results and they will come. One of my students was there for mechanical, Leron. He is now in Melbourne. Leron was working some rotary inverted pendulum. One day he came to me and he told, Dr. Swai, I think my system is chaotic. I looked to him. What I was saying? What I was saying, Leron? How do you know it is chaotic? No, the response is looking such, it is chaotic. I will tell you, if a person comes to you as an academic and he tells you that I am doing some simulations, then I think it is chaotic, you tell him, you close your book, close your computer, go home or go to the Goa beach, then come tomorrow. System is not chaotic, you are a bloody idiot. Got a point? Anything, he is telling, it looks chaotic. What means it looks chaotic? What do you mean that it looks chaotic? Chaotic systems, don't take it, you see, the system, it appears to be random, but completely deterministic. You see the statement I am making here. Chaotic systems appears to be random, but completely deterministic. I will give an example, it will be clear. Suppose there is a agitation going on in the university. Suppose there is a agitation, student agitation going on in the university, and a group of students went to the vice chancellor asking them to you give us this thing, that thing, the examination has to be shifted. Should you give us all A+ grade? That is our demand. So we will not study, we will watch only television, YouTube. That is the agitation. Yesterday night in the hostel, group of 100 students, they made the plan that tomorrow we will go to the vice chancellor office and we will demand it, right? So the plan is there like this. This is the plan. Actually, we have made the plan yesterday that you will go, just give a push to the vice chancellor's door and enter. He will go and from the vice chancellor table, whatever file is there, he will throw it outside. He will go and scold the vice chancellor. This is all plan. All plan. And you people, you will go and stop the vehicles going to the university. All these things have been planned, meticulously planned, nobody knew it. Next day morning, you started doing it. You execute it. I am an outlooker, I am outside, so I will say, what is up? That is chaos. That is chaos. Appears to be random, but completely deterministic. Who is going to do what? It has been planned before. He is not going to push the door. You will do it. He is doing all this task has been assigned, right? All the task has been assigned. So I say chaotic system, that's your order in chaos. Order, got my point? That's your order in chaos. There is an order. So the student says that it appears to be random. No. First find the order. Chaotic system, and always remember, chaotic systems are not random systems. It appears to be random. It is not random. It is completely deterministic. It is completely deterministic. You can determine everything. Random phenomena you cannot determine. So chaotic systems is a bit different. A serious thing, okay, appears to be random, but completely deterministic, right? That's the order in the chaos. Another characteristic is extremely sensitive to initial conditions. Extremely sensitive to initial conditions. Got a point? Slight change, a very minute change, we said butterfly effect, I am not explaining that. It's minute change, the example is given as butterfly effect. That is the Amazon belt, that effect is if that a butterfly affects the wings velocity, that will be a storm in the Indian Ocean. Okay, extremely sensitive to initial conditions, right? But the important point is, chaotic systems appear to be random, but it is deterministic. Another thing is, long-term prediction is not possible. It is deterministic. What is deterministic? The system whose behavior can be predicted precisely. That is deterministic system. Random system, you can do it. Here, prediction is possible, no doubt about that. But long-term prediction is not possible. I'll give an example here. Long-term prediction is not possible. Short-term prediction is possible. Weather forecast, that model is chaotic. Short-term prediction is possible. Suppose I predict the weather, what will happen tomorrow, it will be correct. Day after tomorrow, little wrong. Still day after, it will be almost wrong, right? So long-term prediction not possible, short-term prediction is possible because the model is chaotic. Okay. So another point which we are not discussing here, chaotic systems, it requires a little bit of different mathematics. One is the fractal geometry. Fractal geometry. Have you heard the term of fractal geometry? Fractal geometry. Yeah, Mandelbrot said, yeah, fractal geometry. Yeah, yes. You see, the geometry which we study, and we know that we study, that is the Euclidean geometry. Euclidean geometry, but actually not the Euclidean geometry. This geometry has been developed by Brahmagupta. Now it is proved now. Okay, that is a different issue. There the dimensions are integer dimension. Dimension 1, dimension 2, dimension 3. But in the fractal geometry, we deal with the fractal dimensions. The dimension of something is 2.2, 2.4, 3.5. You got my point? Fractal dimension. So it is meaning is different. I am just giving only one example here. Okay, there is no pen here, that doesn't matter. Now see here. Suppose I have got a piece of paper. What is the dimension? 2. Now I make holes on the paper. I make few holes on the paper. What is the dimension? 2 are the same. A paper without any hole, paper with some holes are the same. They are not same. So how to distinguish this paper with that paper? Euclidean dimension cannot do it. So we have to calculate some fractal dimensions. Okay. Say for example, bread. You get different types of breads, right? So when these breads are produced, you can calculate the fractal dimensions of different breads. Then you will find which breads there are lots of porous things are there, right? So fractal dimension will distinguish these things. So I'll show you something today itself. So fractal geometry is being used to characterize some of the chaotic attractors. Okay. So only thing for you is, so important point to take it before I proceed further. Multiple isolated equilibrium points, energy transport takes place different frequency, limit cycle oscillations, and chaos, right? And chaos. Let's go further. Bifurcations. I am not into. See, chaos occurs. The system will bifurcate. System will bifurcate means like this. You understand this diagram? Do you understand what is the meaning of this diagram? First, this is not a time plot. This is the equilibrium plot. As one of the parameter changes, equilibrium. Now, okay, let me show you. You see here. See this equation, if this parameter R I am changing, you see here, just see the table. If R is equal to 1.9, the output is always 1, 1, 1, 1, 1, 1, 1, right? If R is equal to 1.9, there is only steady state value of 1, right? The moment the R changes to 2.2, now see how it looks. 2.2, 0.7462, 1.1628. Again 0.7462, 1.1628. Again 0.7462, 1.162. So it is in steady state, but two steady states, right? 0.7, 1.16, 0.7, 1.16, 0.7, 1.16. Okay? Period doubling bifurcation, that means two equilibrium points. Two equilibrium points. Now see, if the R changes to 2.48, now see, this one repeats again here, you see. It repeats again. Got my point? Period 4 bifurcations. Okay. So it goes to those, it is not transient. It repeats at certain points. Okay. Now see, this is called the bifurcation phenomena. The system enters into multiple equilibrium points. Okay? And that repeats. And if you plot, you see here, the response looks like this. And if you plot it, the equilibrium points, you see one equilibrium point until this point. Next, there are two equilibrium points. Next, there is 4 equilibrium points. Then there is 8 equilibrium points. Then system enters into chaos. System enters into chaos. These are the equilibrium point plots. Okay. You can see the graph, you can see it. Similarly, this Henon map, okay? So, now, yes. No, Henon map is the system, the different system. This is a different system also, here also bifurcation occurs here, you see there is a bifurcation here, there is bifurcation here. There is chaos here, and there is no chaotic here, you see. As the parameter changes, the things will change. Bifurcation says that if one of the parameter changes, how the equilibrium point changes. How the equilibrium points changes. We'll talk a little bit more about that shortly. How to analyze the nonlinear systems? There are different methods to analyze. One of them is the phase plane method, which I am going to show you now, because phase plane method. That particular method is only applicable for analyzing second order nonlinear systems, because it is a phase plane method. Plane means 2 dimension. It cannot be more than 2 dimension. So you take a nonlinear system or any system, you have 2 second order system. How many state variables will be there? How many state variables? 2. So you just plot those, you get the response, you plot between x1 and x2 and see how it behaves, right? For a linear system, for linear second order system, if the poles are here, real axis, and if you plot the phase plot means you plot x1 versus x2. Not a time plot, remember, not a time plot. x1 versus, you get x1 versus time, x2 versus time, but you plot you give the command, plot x2, x1, no time. Then you will find in the x1, x2 plane or x2, x1 plane maybe, it doesn't matter. If it is like this, depending on the initial conditions, it will look like this. The plot will look like this. So if the plot looks like this, you take a nonlinear system, then you get the response using ODE 45 and plot it. If it is like this, that means the system is stable, and right? If the system has got like this is one of the important, this point, complex conjugate eigenvalues. The phase plane portrait, it looks like this. No, you are not getting it. Now see, I'm telling you, just bear with me. You have got a nonlinear system. You want to analyze what is its behavior, right? So what you do, you go to the computer, you get the response, x1, x2, right? You get x1 versus time, x2 versus time, right? But don't plot x1 versus time and x2 versus time. You get x1 and you get x2, then plot that x1 versus x2, right? If the system has got poles in the complex conjugate negative plot, then this phase plane portrait looks like this. Because unless, how do you interpret? Unless you know from known thing, how can you interpret? I will show you, this is a phase plane portrait. How do you know? Suppose somebody will show me, this is the phase plane portrait, then I will say, it is a damped oscillatory system. The oscillations, it's gradually, it is oscillating, oscillation amplitude is coming down, finally becoming 0. Complex, and this is called stable focus. It has got a name. We will say that the system at that equilibrium point behaves as a stable focus. That means you should know stable focus means the amplitude of oscillation is decreasing. Okay. Just like you see, you must know how a good people behave, how a bad people behave, how a criminal behaves, right? So if you know it, then I will show you the behavior of this system, a person is look like this, then you know, okay, this one matches with an idiot, so that person is idiot. So similar like this. If there is a complex conjugate eigenvalues, the phase plane portrait is a spiral, decreasing spiral. Okay? I'm coming. Yes, yes, I understand. I understand. I understand. I got your point. Very good question. What is saying? This is the system, linear system. Okay. Now here also, the phase plane portrait, if you plot it, it will look like this, right? Another system, it is here, right? Here also, it will look like this, but how to know the difference, right? That you can know it, you see, it is coming down, right? So it will quickly come down. When it will quickly come, when the damping is more, if damping is less, it will slowly come down, right? Many spirals. What happened? So from that you can know it. Whether damping is more or damping is less. Damping is more means away from the geometric axis, sigma. Damping is less means closer, right? So from that you can know. This is just decreasing. Yeah, no damping, I'm coming there. No, if there is no damping, then this is a circle. I'm coming to this point. A circle. Pure oscillations, right? Pure oscillations, if there is no damping, and you change the initial conditions, you will get another circle. Depending on the initial conditions, more, right? Important point, which I'm going to talk now, any closed curve, any closed path in the phase plane indicates system is oscillating. Any closed path indicates there is oscillation. If that closed path is a perfect circle, it is oscillating almost sinusoidally. If it is instead of perfect circle, if the closed path is like this, let us say, then there is no perfect circle. The oscillations has got multiple frequencies, maybe superharmonics and subharmonics, all these things, right? Closed path in the phase plane analysis indicates there is no oscillation. Okay, we are coming to that point. There is that amplitude. No, frequency can find it. Frequency you have to do it some other analysis. See, the right hand side, the response, it is oscillating, the corresponding phase plane portrait. This is a time domain plot, this is these things. Here. Unstable system doesn't matter now. See, close. There is no, you see, all pure oscillations. This is pure oscillations. So this is almost circle or ellipse, doesn't matter. Now, saddle point. Saddle point means one side is positive, another side negative. So it's unstable. This point is important. Now see the difference. This is the Van der Pol oscillator. Limit cycle oscillation. This system exhibits limit cycle oscillations, right? Oscillations. Any oscillations means closed curve. Any oscillations means closed curve. Now see the closed curve here. It is not circular. Is it circular? This is some different shape, right? So it is a limit cycle oscillation. Right? And another point is, isolated closed curve is a limit cycle. What is the meaning of isolated? Isolated means If there are poles here, then phase plane portrait, for a particular initial condition, you simulate it with some initial conditions, you will get this one, right? You change the initial conditions little higher, you will get another circle like this. You change the initial conditions to another value, you will get another circle, right? So these circles are not isolated. By changing the initial conditions, you get different circles. Whereas here, by changing the initial condition, no matter what you do, there is only one circle. You see, I'm drawing it here. You start from this point. You come here. You start from this point. You change the initial conditions. You start from this point. It will not intersect, but I'm just showing here. It will again come to the same point. You start from this point. Again it will come to this point. Not isolated. This is isolated. It's not close, right? Only one closed curve in the phase plane portrait, right? L05 will take only 5 minutes time to talk about the basin of attraction, then I will leave. Analysis, but see here, the interesting thing. Nonlinear systems, this is a very interesting phenomenon. Nonlinear systems can have multiple isolated equilibrium points, right? If a system has got multiple isolated equilibrium points, where it will converge, where it will go, because equilibrium points, if you have got 3 houses, one is Panji, another is near the airport, and another is in the NIT campus. If you have got one house, then you can come to that house only. If you have got multiple houses, where you will go? The system has got 3, see, this particular system has got 3 equilibrium points. Okay, I will explain this diagram. When a system has got multiple equilibrium points, each equilibrium point has got a basin of attraction. I will give an analogy shortly. Each equilibrium point has got a basin of attraction, right? And if you are into that basin, you will be dragged into that equilibrium point. If you are operating in that basin, that means here you see, if the system initial conditions here, it will converge to this equilibrium point. If it is here, it is converged to this point. If it is here and here, this will converge to this point, right? Now see here, I will tell you like this. I will take this example, just you can remember it, okay? Suppose there is a particular person, he has got 3 mistresses. Okay, his wife is there at home and he has got 3 mistresses. Okay, so how many equilibrium points? 4 equilibrium points. The system has got 4 equilibrium points. His wife, mistress number 1, mistress number 2, mistress number 3. His wife lives in NIT Goa campus. Mistress lives, one in Panji, another is Ponda, another in Mupusar, there, right? 3 places. Now the question is, evening time he will go to some place. What is the basin of attraction? If he is driving and he is near the North Goa, he will not come here. He will be attracted to that mistress. The basin of attraction is here. You come here. You will enter there. If he is going to the beach there, near Panji, and the evening comes, it started raining, basin of attraction of that mistress, he will enter into that. Got my point? So the basin of attraction will decide where you are and you will be pulled into that. You got point? The wordings I am using it. If the system is there in the basin of attraction means that mysteries will attract you, right, into that point, right? So in chaotic systems, when you analyze, we always calculate the basin of attraction. It has to be done numerically, not analytically. It's difficult. Okay, it is not difficult. You see, I have calculated these things. I don't know whether I've given the program to you, but if it's there, I can pass it to you. It's not. I'm showing you the basin of attraction here. You see, just a minute. Here, see, basin of attraction. Huh? No, this system, I'll tell you, no. 2 pi 0 minus 2 pi 0, you see, I've done it, you see, this is 0, 0, minus 2 pi 0, plus 2 pi 0. But that is not the point. The question is, you see here, basin of attraction. This is if it operates in this zone, it will be attracted to that. If it operates in this zone, it will go here. If it operates in this zone, it will go there. Okay? Basin of attraction is extremely important. Clear? It has to be done numerically, not analytically. You have to find out the basin of attraction. No, these things I did it 20 years back in my computer, okay? I did not take all the initial conditions. I took some initial condition. It took 2-3 hours in my computer during that time. It takes time. But each initial condition, I will spread therefore it is coming. Otherwise, we can find out. So this is because of that. So we'll take a break now. And the next, any questions here? So nonlinear system analysis, 2 things you should remember. Principle of superposition doesn't hold good, that is okay. But even for linear systems also, principle of superposition doesn't hold good. You have to understand that difference. Energy transport takes place at different frequency. And don't say that it's chaotic. Chaotic is a different phenomenon altogether. You have to do many other analysis to check whether the system is chaotic or not, right? And basin of attraction. If the system is chaotic especially, we have to be very careful what is the basin of attraction. So accordingly, we have to do it. Okay. Thank you very much. I will see in the next lecture the stability.